Let's talk about the physical properties of magmas. The rheology, or the way that magmas or lavas flows, is largely controlled by the viscosity. And the viscosity is illustrated by this image here showing ketchup versus peanut butter. It's clear that peanut butter is much more viscous than ketchup, meaning that it is more resistant to flow. So ketchup is less viscous than the peanut butter. And we can talk about magmas and lavas in the same way. And viscosity is controlled by several factors, but importantly, temperature, the composition, the bubble and the crystal content, and the water content are the most important. Pressure has a slight effect. An increase in pressure, meaning if a magma is buried more deeply, will have a slight effect of reducing the viscosity of a magma. But the other factors are more important, so let's focus on those. Temperature has the effect of decreasing the viscosity. So an increase in temperature has a decrease in viscosity, and we use the Greek letter eta for that. The composition is important. In particular, the higher the silica content, the higher the viscosity. Likewise, the amount of volatiles in a magma or a lava. So an increase in the volatiles equals an increase in the viscosity, eta. The bubble and crystal content have a similar effect. The more bubbles and crystals the higher the viscosity. The water content has the opposite effect. The more water in a magma or lava has the effect of reducing the viscosity. So let's walk through all of this and see what more detail we can get into. Let's just look at the various properties of magmas, and this is on the left-hand side of this diagram is looking at more mafic lavas versus more felsic lavas or magmas. So we're starting with a basaltic lava or a basaltic magma. Those have silica contents on the order of 50%. And those lavas are also very hot in comparison to felsic lavas. So hot meaning 1,000 to about 1,200 degrees Celsius. And these are very runny, thin, not very viscous lavas. We can compare that to rhyolitic lavas that have a silica content on the order of 70% and are much cooler, so 800 to 1,000 degrees Celsius. And these are much thicker and stickier lavas, so much more viscous. The effect of the silica on the viscosity results from the effect that the silica tetrahedra that form many of the bonds that are in silicate minerals in these melts form networks of tetrahedra that increase the viscosity. There are other components in lavas that include the major elements that bond with the silica tetrahedra or fill spaces between silica tetrahedra. Those have the effect of reducing viscosity, but let's just have a look at the next diagram that goes into a little more detail. We don't need to read all of this, but the reason I have this here is because if you look at just a pure silica network, we have a network of, let's say, quartz. And the silica tetrahedra bond and form structures that resist flow, whereas more modifiers like potassium, sodium, calcium, magnesium, and iron fill in some of the spaces between the silica tetrahedra and allow a more open structure and reduce the viscosity and allow a lava or magma to flow more easily. If we look at plots of viscosity versus some of these properties, let's first look here at a plot of viscosity versus silica content. And what you see are the basaltic lavas here on the left near 50% silica, the rhyolites here near 70% silica. And you see these lines showing the effect of viscosity versus temperature. And what you see is that for a basaltic lava that is typically 1200 to 1000 degrees Celsius, so in this range, the viscosities are much lower than a rhyolitic lava that is 800 to 1000 degrees Celsius and has much higher viscosities. Then we can look at this plot of viscosity versus temperature. And this is just a basalt lava as an example. And what you see is that the viscosity increases as temperature decreases. So this x-axis goes from 1400 degrees Celsius and cools to the right. So the viscosity is increasing until a point somewhere around 1200 degrees Celsius where crystallization begins. And then you see that the slope of the line increases more markedly and viscosity starts to increase even more. So we're seeing two effects here. We're seeing a temperature effect in viscosity increasing with decreasing temperature, and we're seeing the effect of crystallization. So the presence of crystals really increases the viscosity of that basaltic lava. Then we can look at a plot of viscosity versus the percentage of water, and this is an example in a rhyolite lava at 1000 degrees Celsius. And what you see is that with an increase of water from 0 to 10%, you see the viscosity decrease over that percentage range. So the presence of the water in that melt decreases that viscosity. Now, if we just look at viscosity again versus temperature and different composition lavas, we'll see again basalt lavas here at higher temperatures, so above 1200 degrees Celsius. You see the viscosity decreases with higher temperatures and increases at lower temperatures. And this curve here reflects the beginning of crystallization. So viscosity is going to increase around 1200 degrees Celsius when the basaltic lava starts to crystallize. And we see in comparison a rhyolitic obsidian lava, either one of these curves, is more viscous than the basalt. And the difference between these two obsidian curves is one is dry and one has 6% water in it. And you see that the viscosity is lower in the rhyolitic lava that has 6% water. So that's the water effect. We see viscosity change in basaltic lavas within the same flow. If you start off with a pohoi lava that is ropey and runny and not terribly viscous, and you either start to crystallize or gases start to exsolve, increasing the viscosity, or you consider the slope on which the lava is flowing. The higher the slope, the steeper the slope, the greater the shear rate, or the greater the rate of flow in that lava. That has the effect of increasing the viscosity. So if we start with a pohoi lava that is thin and runny, and it starts to flow downhill at a steeper angle, it is going to transition into an flow. The viscosity will change. And looking at mafic to felsic magmas, this summarizes some of these properties we've been talking about. The mafic magma has the lowest silica content, and the effect of that is it has a low viscosity. The gas content is lower, also having an effect on the viscosity. It's not explosive, and so it doesn't tend to form pyroclastic material. And it forms these shield volcanoes or cinder cones that are only mildly explosive. Whereas felsic magmas have a high silica content, around 70%, are the most viscous. They have gas contents on the range of 4 to 6% or higher. They are the lavas that tend to form the greatest tendency to form pyroclastic material, and they form explosive eruptions, either pyroclastic flows or very thick, sticky lavas that form volcanic domes, like Panem crater and obsidian flows that are thick and sticky and viscous. If we look at the kinds of volatiles, that means dissolved gases, that are in these melts, you'll see that rhyolitic magmas have the largest volume of the volatiles in rhyolitic magmas is made up of water, followed by carbon dioxide, sulfur dioxide, and some fluorine. This is different from the volatiles that are in a basalt magma. Mostly carbon dioxide, followed by water, sulfur dioxide, fluorine, chlorine, and some other gases. This plot shows the percentage of volatiles on the y-axis versus the silica content. And so we have rhyolites on this side of the plot and basalts on this side of the plot. And what you see is that there is an increase in the percentage volatiles that you expect to see that corresponds to an increase in the silica content. Different composition melts that form in different tectonic environments have different percentages of water concentrations. And if we look at just some examples of basalts, mid-ocean ridge basalt is a morb, and other island arc basalts have very small percentage of water, so somewhere around 1% or less. Basalts that form above subduction zones are slightly higher, at 2 to 4%. And then we can skip down to the intermediate magmas, looking at andesites or dacite that have 1 to 5% water. And then rhyolites have a much higher percentage, up to about 7% water. Then if we look at the effect of pressure on dissolved gases, we see this plot has pressure on the x-axis, so higher pressure on the left to lower pressures on the right. So you can consider this deeper magmas versus shallow magmas. And then the volume of those dissolved gases as they exsolve on the y-axis and increasing in volume on the right-hand side. So this refers to the size of the bubbles that are formed as gases are exsolved out of the magma. And the point of this graph really is that as you see a decrease in pressure on a magma, so a magma rising up through the earth, either as an eruption is starting or as it just moves through earth, we see that the volume of those bubbles increases exponentially when you get near to the surface of the earth. And really the point here is that if you have a rapid decrease in pressure in one of these magmas, it would lead to a sudden increase in the size of the bubbles from exhaled gases. So really what this is saying is if you have a Mount St. Helens type eruption where a landslide that's triggered by seismicity from magma motion beneath ground or from whatever reason, a landslide happens, decreases the pressure on an underlying magma body, suddenly the bubble size increases rapidly, and that leads to an explosive eruption. And the other thing to consider too is that if it's a rhyolitic magma, it's trapping those gases in the magma longer. Those bubbles can't escape. Those gases can't escape. They're trapped in that rhyolitic magma that's thick and sticky and viscous, and it's not degassing slowly and gently like you might see in a basaltic magma. So again, these gases lead to not only an increase in viscosity, but an increase in explosivity of these magmas.